In theoretical physics, the vacuum catastrophe stands as the most famously embarrassing prediction in the history of the field. Quantum mechanics predicts an empty space energy, contradicting reality by 10 to the power of 122. To resolve this, standard cosmology treats the universe as a volume, inventing invisible fluids like dark energy to fill the space. This bloated fluid model assumes the error lies in our understanding of the contents. However, the true mistake may be the dimension we are measuring. We are applying volumetric math to a phenomenon that exists at the boundary. Independent researcher Nadav Bashan identifies this as a dimensional category error. His framework, the macroscopic boundary principle, argues that large-scale systems are governed strictly by the geometry of their two-dimensional outer boundaries, rather than the three-dimensional chaos of their internal volumes. To understand the universe, we must look past the contents of the fishbowl and measure the geometry of the glass itself. This boundary logic is visible locally at the surface of every star. A star's photosphere serves as a decoupling surface, the two-dimensional boundary where photons finally escape the internal bulk. When we evaluate a star's radiative output against its gravitational retention, the internal bulk mass and surface gravity cancel each other out identically. This leaves a pure, dimensionless geometric capacity of pi cubed over 15. Data from a kinematic sample of 190 stars proves this isn't just theory. Regardless of their size or mass, their radiative output clusters just below this horizontal ceiling of pi cubed over 15. This represents a scale invariant law of the envelope. If the boundary is spherical, the geometry dictates the limit. We can scale this same logic to the cosmic horizon, the ultimate two-dimensional boundary of our observable universe. Physics has long recognized that the cosmic horizon behaves as a thermodynamic boundary, possessing a well-defined temperature and entropy. If the cosmic horizon is a spherical boundary identical in geometry to a star's surface, we must ask why its mathematical normalization would differ. When we project the stellar boundary constant, pi cubed over 15, into the three-dimensional volume of the cosmos, we apply an exact geometric factor of 1/3. This represents the fixed ratio required to map a two-dimensional surface capacity into a three-dimensional parameter. Dividing our boundary constant by 3 yields a value of pi cubed over 45. This calculation results in a dark energy fraction of roughly 0.69, matching the astronomical observations of our universe without tuning any parameters. In this framework, the 10 to the 122 vacuum discrepancy is a discrete count. It measures how many microscopic Planck areas are required to tile the macroscopic two-dimensional horizon. The greatest mathematical gap in physics arose from a scaling artifact, the attempt to compare a two-dimensional boundary limit to a three-dimensional bulk volume. This logic erases the need for invisible particles. Shifting normalization from the bulk to the boundary resolves the math. Constants like gravity and the cosmological constant form a geometric bridge, linking the microscopic Planck scale to the macroscopic horizon. This framework also removes the infinite density of the Big Bang singularity. The universe began at a finite minimum boundary scale, the smallest horizon capable of supporting thermal radiation. This provides a finite initial entropy and defines the direction of time. The universe functions as a stable holographic structure, anchored by the fixed geometry of its edge. We are living inside a boundary-constraint system, where the rules are written on the glass.